AC analysis, introduction to AC and resonance. We are coming to another important part of the networks. In this slot we have so many topics. This is called AC analysis. For example, we studied introduction to networks. Part 2 is general analysis technique. Part 3 specific analysis technique. Part 4 transient analysis. This is part 5 AC analysis. In this we have mainly 5 topics: introduction to AC analysis, resonance, phasor analysis, sinusoidal steady state analysis, then finally coupled circuits. These are the 5 topics that we have in this AC analysis. Of course, filters is also there, but filters is for EEE. EC people do not have that, but it's good for EC people also to study, because some public sector exams they are asking even for EC, but for GATE exam filters is not there for EC. That's why I have taken this 5. We'll study that as a separate topic, which is useful for GATE, EEE, and for public sector for all 3 branches, EC, EEE, and instrumentation. So that's our target of this lecture, and target group are those branches. Now let's see the introduction. In introduction, the first thing is rectangular form. For example, if there is an impedance called R plus JX, R is a real part, X is a reactance part, and if the reactance is due to inductor j omega L, due to capacitive 1 by j omega C. So this is reactance of inductor and capacitor. Any circuit consists of both reactive elements, then the resultant should be taken. The resultant is taken as XL and XC difference. This is not minus, this is difference. Why do I say difference? Sometimes XL may be higher, sometimes XC may be higher, but the resultant is difference of those two. That's the small idea about rectangular form. Then coming to polar form, an impedance is Z angle theta, where small z is an amplitude, theta is a phase angle. In the rectangle form, we can convert into polar form. Take your Z is equal to RJX, Z is Z angle theta. That means R is equal to Z cos theta, X is Z sin theta. The small z is root of x square plus y square. Theta is tan inverse of x by R. Tan inverse of real term by imaginary term by real term you have to take. For any tan is opposite by adjacent. That conversion you can take. Then operations. Suppose you have addition. How do you add them? Subtraction. Addition, subtraction is done in real rectangle form. Multiplication and division is done in polar form. When you say Z1 plus Z2, X1 plus X2, J, Y1 and Y2. If you multiply R1, R2, angle theta 1 plus theta 2. If you divide R1 by R2, angle theta 1 minus theta 2. So please follow these notations as we are going to analyze in AC analysis. In fact, I gave this small introduction of AC at the beginning itself. Why? In every topic we have studied AC. That's why I gave a small introduction there. But now it is purely AC analysis. Then, one important point. I have given the conversions for rectangle to polar, polar to rectangle. The reality is you don't need to do like what equations I gave. You can directly use your calculator. In calculator you have rectangle to polar and polar to rectangle. This is what we have. So you don't need to calculate manually. Calculator itself will give you direct answer. So you make use of that facility that are there already in calculator, and you can make things very, very fast in the exam. Now AC sources. AC sources are given by sinusoidal symbol. This is current source, voltage source here, current source here. Magnitude, angle, magnitude, angle. Remember, we will always say Vm cos omega t plus theta. Here, Vm angle theta is one way of representation. Vm cos is another way of representation. So when the frequency is required, they will give frequency. If frequency is not required, you can convert into polar form. So a given trigonometric equation, you can put in the polar form. That's a small idea about AC sources. Note, very important note I have made. In all AC circuits, operating frequency is same, because the electric circuits are linear. When the circuit is linear, frequency will never change. So remember, this is a very important precaution. Then what are we going to do in all these calculations and analysis? If the frequency is same, you are only going to calculate magnitude and phase. Input magnitude, output magnitude is going to be different. Input phase and output phase are going to be different, because only one thing is going to be same, is frequency. That's why that's a very important note, important observation. Then as the frequency is fixed, we are going to calculate magnitude and phase angle. After calculating the magnitude and phase angle, the response should be in the form of excitation. What do I mean by this third point? If the excitation is given in terms of sine, it should be, the response also should be in terms of sine. If it is given in the form of polar form, it should be in the polar form. So before you conclude the answer, you always say, put the answer in terms of the input. Calculate the amplitude, calculate the phase angle, then adjust the answer in the form of the input. These are the three important precautions you need to follow as a custom, as a necessary, in order to do the better calculations and better answers. So this is small introduction to AC. Then I am going to take you to resonance circuits. Please understand, in transients we have seen the great application called switching. In AC we are seeing another application, very important application called resonance. The word resonance means two things are in line. It's very interesting. This word resonance is not from electrical circuits or engineering. It is there in sound also. It is there in physics. The word resonance was started in intermediate physics or in physics when you have taken a column, air column, and the frequency of the fork, if you hit, the maximum sound come. There are two important things here. There is one thing called natural frequency, another thing called forced frequency. Natural frequency means what is the frequency of the circuit. Forced frequency means what is the frequency you are giving. So what frequency you are giving, if it is equal to the frequency of the circuit, then we say they are in resonance. In sound, maximum sound came. In electrical circuits we call it as maximum current will come. So there are whenever you hear the word resonance in general, either in engineering or in physics or in day-to-day life, it only means one thing: maximum output comes. So for example, here there are two types of resonance circuits. Series resonance circuit, which gives maximum current. Parallel resonance circuit will give maximum impedance. If the word maximum is not there, that's not resonance. I'll give another examples in day-to-day life. When a teacher is teaching and students are listening, there may be 100 students listening, but only few of them understand. And when they understand, their face will glow. that shows maximum smile will come. That means when the teacher is going on teaching at one particular point, student will understand. So when we are talking certain things to people, when they understand, their face will glow. Then we can understand that person is able to understand what we are speaking. So that is called a resonance between student and teacher. So teaching principles has the same. Same thing can occur in any approach, in any relationship. Whenever two people are there, when they understand each other, the maximum glow or maximum smile, maximum you can see the face. So this is basic definition. That's why the resonance we call sound resonance, the resonance between people we call, and finally we are talking about electrical resonance. But remember one thing, maximum current should come. If maximum impedance is coming, in the parallel resonance circuit, when impedance is maximum, current is going to be minimum. So series resonance is generally called resonance. Parallel resonance is called anti-resonance. Why it is called anti? Because the current is less there. So when the current is less, we call it as anti-resonance. So please understand, parallel resonance most of the time elderly people they call it as anti because current is minimum, because it is behaving opposite to resonance. Now let me take you to series resonance circuit. Let us consider a series resonance circuit RLC here. Its impedance is equal to R plus JXL minus XC. Why minus? Because capacitor is minus. Now I am going to make some cases. If XL is lesser, the circuit will become capacitive, negative. If XL is more, capacitive circuit will become positive. Positive means inductive. If both are equal, the circuit becomes resistive because the values will cancel. XL and XC will cancel. It will be purely left as resistive. When it is left as resistive, we call it as resonance. Now calculate. XL is equal to XC. Omega naught L is equal to 1 by omega naught C. Please observe. If you see here, generally we will say omega omega everywhere. But when the resonance occurs, we call it as omega naught. This is one of the important precautions in the entire chapter of resonance. For example, I can say omega L, but I say omega naught because omega L is equal to 1 by omega naught C only at resonance. That's why O for resonance. Then calculate, cross multiply and all that, 1 by root of LC. That's called resonant frequency. This is a very simple way of achieving a resonant frequency. In fact, let them give for any circuit and we are going to have resonance frequency by saying put J term 0. Calculate impedance, put J term 0. That's the simplest way of calculating resonant frequency. Now let me take you to quality factor. This is a very important factor. And one day I was asking, what is the quality of a quality factor? What's the quality? Suppose you have an inductor. Every inductor will have some resistance in general, in series, by mistake. The quality of the inductor is the more energy stored but less dissipation. Suppose an ideal inductor, there is no internal resistance. So the definition is 2 pi into energy stored by energy dissipated. Energy stored should be more if inductor is good. Energy dissipated should be 0. If energy dissipated is 0, that means the resistance is not there, then quality factor is infinity. So quality factor can go even up to infinity ideally. But practically quality factor is always changing between 10 to 100. It cannot go beyond 100. The whole world is struggling for this. We have seen in resonance the rise time was a very important factor. Here quality factor is very important. The whole world is stuck up at one word, how to increase the quality factor. If you want to increase the quality factor, the best thing is make a ideal inductor. That's the meaning. So quality factor after calculating will become as 1 by omega RC omega L by R. In general, you can simply say X by R. This equation finalized as reactance by resistance. Okay. So let us use this quality factor in our further discussions.